Hi there, welcome back to the Cosmic Classroom. This week I want to talk to you about white dwarfs, which are the remains of very low mass stars. If you recall, I made a video on low mass stars a couple weeks ago, which would be very relevant to this if you want to link the two things together. So white dwarfs are what's left from a low mass star when it dies. So it's the core of that star after it ejects the planetary nebula. So what we're looking at is directly this very hot core where fusion used to be happening. So it's very hot, it's very small, you're looking only at the core of the star, and it's extremely dense. So imagine packing the mass of the sun into a region about the size of the Earth. But you don't really have an idea about how big the sun is really. So how about try to imagine packing almost 100 people in one teaspoon. Squeeze them all in there. That's how dense a white dwarf is. So, and what stops gravity, what stops this white dwarf from collapsing completely is the degeneracy pressure that we talked about before. In this case, it's electron degeneracy pressure, which is, you can think about it as just the atoms are so close together that it's very hard to make them even closer together. Now, white dwarfs are funny because white dwarfs are made of degenerate matter. The more massive the white dwarf becomes, or the more massive the white dwarf is, the smaller it is, because there is more pressure compressing it more and more, making that matter more and more degenerate. So if you were to look at a white dwarf of about about the mass of the sun, it would look slightly bigger than the Earth. But if you were to add more and more mass to it, it would become smaller and smaller and smaller. So what I have here is a plot that shows you in the x-axis the stellar mass of the remainder of the core. The star used to be more massive than that. And the stellar radius, the radius of the white dwarf. As the mass increases, the radius decreases, which is very counterintuitive. And if the star ever achieves a mass of 1.4 solar masses, it collapses in itself. It explodes in a supernova. So the reason why the star doesn't start fusing carbon or doesn't start fusing heavier elements, it's because it never achieves a temperature that's hot enough to start fusing the elements. So instead the star just explodes. Now there are different kinds of white dwarfs, which I'll get to in a minute. So the composition of a white dwarf will depend on the mass of that initial star. If that initial star was very low mass, maybe the white dwarf would be made mostly of helium. It never got hot enough for it to fuse helium into carbon. So what you have is a white dwarf which is made mostly of helium. If the star is more massive, it's able to fuse elements all the way up to carbon, and what's left is this core of carbon. And if it's intermediate mass stars, you can have carbon, oxygen, and heavier elements in it. So there are a lot of white dwarfs, but it's hard to observe them because they are extremely dim. Even though they are hot, they are dim because they're very small. And if nothing else happens to them, if they're just left there alone, they will start cooling down, losing some of the heat to space, and becoming darker and darker and darker. So the end of a white dwarf is what we call a black dwarf. But let's be careful here with the word black. The star never really becomes completely black, because in order to do that, it would have to lose all its energy, right? It becomes more similar to a brown dwarf than to a black dwarf. But the idea is it loses the luminosity, becomes very dark and very hard to observe. Now, one more thing to keep in mind. Because white dwarfs are the result of the life of low mass stars, and because low mass stars live shorter lives than higher mass stars. For example, a white dwarf that will result from the evolution of a star with the mass of the sun. The star has to live 10 billion years before achieving that stage. So there are stars that are low mass enough that we can't possibly observe white dwarfs that came from those stars, because the universe is just not old enough to observe them. So every time you observe a white dwarf, it's a very old object because it already went through all its life as in the main sequence. And it's probably the result of an object that was formed right in the beginning of the universe, in the first few billion years of the universe. So I think this is what I wanted to tell you about white dwarfs, and I hope it helped.